Hi, I'm Sergey Nikolaev, CEO of Manticore Search. Today I'll show how vector quantization helps make vector search faster and more efficient, cutting memory use and speeding up queries without losing much accuracy. Let's get started. Before we talk about quantization, let's define the objects we're searching. Whatever pipeline you use, self-hosted embeddings model, a hosted API, or embeddings shipped with the content, every document ends up as a dense vector. That vector is just a list of a few 132-bit floats capturing the document semantics. Many modern models go even further with 768, 1024 or more dimensions, which makes things even heavier. One vector is tiny, but at production scale we store billions. 1,384 dimension vectors weigh in at roughly 1.4 terabyte if we keep them in full precision, and renting that much high-performance RAM is eye-watering. Search is even tougher than storage. The basic way is to compare the query vector to all stored vectors. This takes big O of n times d operations, billions of dot products for a single request, which is out of reach for real-time systems. We lean on indexes like HNSW to skip most of those comparisons. The graph usually needs only a few hundred distance checks, yet every hop still pulls full-size vectors across the memory bus, and the graph's own links add more bytes. At billion scale, the random memory access slows things down and increases hardware costs. So the first bottleneck isn't clever algorithms, it's data size. Making the vectors smaller is the key to improving everything else. To decide which documents are nearest, we need a distance formula. For text embeddings, the usual suspects are L2, cosine, and dot product. All three require the raw coordinate values of the vectors. You can't calculate them from a simple ID or a bit hash. Baseline accelerators add structure so we don't touch every vector. HNSW builds a small world graph. At query time, we hop from a high-level entry down to neighboring nodes, stopping after a few hundred distance checks instead of billions. That's great for latency, but each hop still fetches the full 32-bit vector, and the graph's extra links can double or triple memory use. IVF, the inverted file approach, first clusters the space into thousands of buckets. A query lands in the few buckets whose centroids are closest, and we scan only those vectors. It's cheaper to store than HNSW, but if the true neighbor lives in a different bucket, recall drops. Again, every candidate is examined in full precision. So HNSW and IVF reduce the number of comparisons, but every comparison still moves full-size floats across the memory bus. At billion scale, that memory traffic, not arithmetic, becomes the real bottleneck. Shrinking the vectors themselves is the next logical step, and that's where quantization changes the game. Embeddings carry a lot of signal but also plenty of redundancy. A few bits of noise in one coordinate almost never change who the nearest neighbor is, so storing all numbers with full 32-bit precision wastes space. When we compress those numbers, three good things happen. First, the data shrink. Dropping each component to 8 bits cuts the footprint by a factor of 4. 4 bits buys us an 8-fold cut, and a single bit slashes size 32 times. If we use product quantization, we can often chop memory 90+%. Imagine 4000 bytes collapsing to just 8. Second, the whole index fits in fast memory. 1,384 dimension vectors in PQ form no longer need 1.4 terabytes. They fit in well under 50 gigabytes. That means fewer servers, fewer cache misses, and no paging to slow us down. Third, queries run cheaper and faster. Once vectors are tiny, distance becomes a handful of table lookups, or at the 1-bit extreme, one XOR followed by a popcnt. Those two instructions are hardwired into modern CPUs and run across wide SIMD lanes, so throughput jumps while the cloud bill drops. Yes, we surrender a little numeric precision, but we buy orders of magnitude more speed and a huge cut in hardware spend. Quantization turns vector search from a memory-bound bottleneck into a lean, real-time service. Scalar quantization is just fancy rounding. Start by taking every float in the vector and snapping it to the nearest bucket. If we allow 256 buckets, we need 8 bits. 16 buckets need 4 bits, and if we only care about the sign, positive or negative, that's a single bit. The size drop is dramatic. For a 384-dimension text vector at 8 bits, the record falls from 1536 bytes to 384 bytes, 4 times smaller. At 4 bits, it's 192 bytes and 8-fold cut. At 1 bit, it's just 48 bytes, 32 times smaller. What about accuracy? We keep a couple of miniature numbers for each bucket, a scale and an offset. During search, we lock them up and slip them back into the L2 or cosine formula. That patch puts the distance almost back where it would have been with full floats. We'll talk about it in detail shortly. In practice, halving to FP16 or quartering to 8 bits barely nudges recall and costs 0 speed. Going down to 4 bits or even 1 bit does blur things, but the vectors are so small and the math so cheap that we can pull a larger candidate set and re-rank it with the original floats. The net result: huge memory savings, lightning fast first pass, and after rescoring we still deliver the right answers. 1 bit is the most aggressive form of scalar quantization. We save only the sign of every coordinate. Positive becomes 1, negative or 0 becomes 0. A 394-dimensional float vector shrinks from 1.5 kilobyte to just 48 byte. How do we measure similarity with so little information? 2 hardware tricks. XOR. Give me a 1 whenever the query bit and the index bit differ. PopCNT. A built-in CPU instruction that counts how many ones are set in a word. Run XOR on the 2-bit strings, send the result to PopCNT, and you get the Hamming distance in 2 CPU clock cycles. Because modern CPUs offer SIMD, single instruction multiple data, we process dozens of coordinates at once. The whole vector fits in a couple of registers, no RAM fetch, no cache miss. You might expect accuracy to collapse, but even plain sign hashing gets us to around 0.65 recall at 10. That means if we look at the top 10 results returned, there is a 65% chance the correct one is in there. It's not perfect, but for a 1-bit index, that's a strong start. Now let's make 2 small but powerful tweaks. First, recentering. Instead of taking the sign around 0, we learn the actual center of each dimension during training. That way, when we store the sign bit, it reflects the real data distribution, cutting angle error almost in half. We'll talk about this technique in more detail shortly. Second, asymmetric querying. The stored index stays at 1 bit per value, but the incoming query keeps 4 bits of resolution. This adds nuance without bloating the index, and it nudges the recall up by several points. Finally, we rescore the top results using the original full precision vectors. That last step fills in any gaps, bringing the recall up to around 0.9, and NDCG, how well we rank the results, up to about 0.95. So 1-bit scalar quantization turns distance into just 2 fast instructions, keeps the index tiny enough to live entirely in cache, and still delivers a short list that's nearly as good as full precision. Scalar quantization trimmed every individual number. Product quantization compresses the whole vector. Let's walk through it with round numbers. Imagine each embedding has 1024 dimensions. Any large size works, but 1024 keeps the math tidy. First, we slice the vector into, say, 8 equal blocks, so each block holds 128 values. If your vectors were, for example, 768 dimensional, you might use 6 blocks of 128 instead. The point is, break the long vector into smaller, fixed-length pieces. Next, we look at one block position across the entire dataset. We gather all those 128 value slices and run plain k-means clustering. A common choice is to create 256 centroids, our representative vectors, because that number fits neatly in 1 byte. Want more precision? Use more centroids and spend 2 bytes instead. When we store a vector, we don't store the actual block anymore. Instead, for each block, we find which centroid it's closest to and store just the index, the ID of that centroid. Since each ID is 1 byte and we have 8 blocks, the original 4 kilobyte vector shrinks to just 8 bytes. That's a 500x reduction. When a query comes in, we don't compare it to the raw stored vectors. Instead, we split the query into the same number of blocks, 8 in this case, and compare each query block to all 256 centroids for that block position. We do this once per query block and build a small table. Query block 1 is this far from centroid 0, centroid 1, centroid 2, and so on. Now, to compare the query to a stored vector, we use the centroid IDs that were saved during compression. For each block, the stored vector just says, I'm closest to centroid 42, so we look up distance to centroid 42 in the queries table. Do this for all blocks, collect 8 distances and add them up. That's your total estimated distance. No big calculations, no need to load large vectors from memory, just a few fast table lookups, and then we sum those 8 numbers. And since the entire lookup table fits in fast CPU cache, the process stays lightning fast. Unfortunately, this method comes with some drawbacks. The centroids are trained offline. If your data distribution changes, you'll need to retrain and re-encode. And because compression introduces a little error, production systems often fetch extra candidates and rank them using the original floats to restore full recall. Up to now, our product quantization used 1 codebook per block, 256 centroids, and a 1 byte index. Sometimes, though, we want a little more recall without spending a single extra byte. That's where multi-codebook tricks come in. First, a quick reminder. A codebook is just a lookup table of tiny vectors. During encoding, we keep only the table index, not the vector itself. Residual vector quantization, RVQ, is the simplest add-on. Pick a core centroid, subtract it off, and quantize the residual with a second codebook. Repeat if you like. Each stage chops the error down, so 3 8-bit stages can get you near full precision recall while still costing only 24 bytes. Optimized PQ, OPQ, is another add-on. Before running plain PQ, rotate the vector space so variance is spread evenly across blocks. Storage cost is unchanged, but reconstruction error drops 10 to 20%. And yes, the classical SH locality-sensitive hashing still turns up in ultra-low latency systems. It's data-independent and lightning fast to build, but it needs more bits to match the accuracy of the learned methods. The trade-off is more codebooks or a clever rotation mean heavier offline training and a few extra additions at query time, but you squeeze far better accuracy out of exactly the same memory. So when you've already shrunk vectors as far as they'll go and still need a few more points of recall, these multi-codebook tricks are the next lever to pull. So, scalar and product quantization usually use the same level of precision, both when storing the data and when running a query. But here is the thing, we can actually cheat a little. We can store the index in a super compact format to save space, but then query it using a more detailed, high precision code. This trick is called asymmetric quantization. Let me show you a quick example of how this works in practice. First, we quantize every vector down to just 4 bits and use those to build our HNSW graph. Now, those 4-bit vectors aren't super precise, but they are good enough for the graph to find decent neighbors. Once the graph structure is set, meaning all the links are in place, we can actually throw away most of the data. We drop the 4-bit values and keep only the 1-bit signs. The graph itself doesn't change, but now the stored vectors are 32 times smaller. Pretty cool, right? When it's time to run a query, we still quantize the live query to 4 bits. so it actually holds more detail than the 1-bit vectors in the graph. We navigate the graph using the usual XOR plus POP-CNT trick on those 1-bit signs. And because the query is a bit richer, we get a nice little boost in recall, a few extra points. Then, to clean up any remaining error, we do a final rerank using the original float values. So, asymmetric quantization helps us get a really small index, which is great, but here it comes with a few trade-offs. First off, the build process isn't exactly simple. It's a two-step thing. We quantize to 4 bits, then build the graph, and after that we downshift it all to 1 bit. That extra step adds some time to indexing. Then there is the temporary storage we need. While we're building, that 4-bit version sticks around. It's just temporary, but we're talking tens of gigabytes. Not something you'll need in production, but something you have to plan for. Another thing is updates. They get kind of awkward. If you've got new data, you either have to rebuild the whole thing or inject it straight at 1 bit. And doing that at 1 bit weakens the graph connections a bit. And finally, accuracy takes a hit. Once those links are stored at just 1 bit, we lose a lot of the fine detail. So we have to lean on the oversampling and reranking to pull back the top results. So small index, yes, but not without some headaches along the way. Alright, so quantization helps make search faster and more efficient, which is great. But there is a trade-off. It kind of bends the math a bit. Things get a little precise. Now this next part is really about fixing that. We can't fully uncompress the vectors. That's just not how it works. But what we can do is adjust their shape just enough to make the rankings more accurate. Take this 8-bit bucket here, the yellow one. With plain scalar quantization, every value inside it gets treated as the blue dot in the center, basically the average or the midpoint of the bucket. But in real life, real data like these gray dots, they almost never land exactly on that center point. They land to bunch up a bit off to the side, like a little to the left here. And that shift, that bias, it messes with the similarity scores. It makes them less accurate. So, how do we fix it? Well, during training, we learn 2 numbers for each bucket. A shift which slides the stored value over to where the real average is, that's the red dot, and the stretch, which widens or squeezes the bucket if the values are spread out unevenly. And we do this for every bucket, so 256 of them in 8-bit, 16 in 4-bit, and just 2 in 1-bit. At query time, we simply look these values up. It only takes a few cache reads, so the cost is tiny. The beauty of this approach is that all this metadata is shared. Whether you're using cosine or L2 distance, you only need like 2 or 3 32-bit floats per dimension, not per vector. So even if you're working with a billion vectors, the extra memory is basically nothing, well under 1% of RAM. But it still wins you back 2 to 5 points of recall, which is kind of amazing. And actually, the exact same idea works for 1-bit hashing too. See, 0, that blue line, isn't always the best place to split positives from negatives. So instead, we first learn the real center for each dimension, that's the red line, and then store just the sign relative to that. You still get the same tiny 1-bit payload, but the angle error, it's almost cut in half. Now there are a couple of small trade-offs with this approach. First, you'll need to run 1 extra training pass to generate those tweak tables. And if your data changes over time, you'll want to update those numbers now and then. Also at query time, it takes a few extra microseconds to look up the tweaks. But overall, the gains usually far outweigh the costs. Alright, so even with all the calibration tricks we just talked about, a heavily quantized index can still miss the perfect neighbor once in a while. That's where the insurance policy comes in, a 2-stage pipeline. First we oversample, then we rescore. Let's say the user wants the top 10 results. Instead of stopping at 10, we grab say 50 or even 100 candidates from the quantized index, whether it's HNSW or IVFPQ, no matter. The reason we can afford to do that is because these compressed vectors are super lightweight and the distance calculations are just fast XORs and table lookups. So pulling an extra 90 isn't really a big deal, it's almost free. Next, for that short list of candidates, we fetch the original 32-bit embeddings, which might be sitting in a cooler memory tier, like slower RAM or even on SSD. But we are only talking about a few kilobytes here, so the I/O overhead is minimal. Then we do the exact distance calculation, cosine or all2, re-rank the results, and return the real top 10. Why does it work so well? Because over 90% of the latency is in that first pass, and we've already sped it up dramatically thanks to quantization. The rescoring stage only touches a tiny slice of the whole dataset, maybe 1/1000th of a percent, so it just adds a few milliseconds. But that's enough to push the recall super close to what you'd get with full precision search. So yeah, oversample and rescore. You get the speed and memory benefits of quantization and the accuracy that's good enough for production. Alright, so we've covered the concepts, but let's look at how this plays out in the real world. First up, Pinecone. They replaced 32-bit vectors with 8-byte product quantization codes and added an IVF frontend. The result, memory usage dropped by 97%. And query times, they got 92 times faster. We're talking about going from seconds down to well under 50 milliseconds. That's a huge win. Now let's scale things up, say to 1 billion vectors on AWS OpenSearch. They tested the KNN plugin comparing standard float precision HNSW with the version that used product quantization. The recall stayed the same, but the PQ version used just a tenth of the RAM. And the cluster cost? It dropped by around 90%. That's serious savings at scale. Now let's look at Melvus. They compared the standard full precision index with RabbitQ, a compact 1-bit quantization method, but not just plain sign hashing. RabbitQ adds a few clever refinements. It learns where the true center of each dimension lies and applies the lightweight corrections we discussed earlier, so the 1-bit signs still preserve important angles. The result? Memory drops by 97%, throughput nearly triples, and recall still stays above 76%. That's solid accuracy with a fraction of the hardware. Quantization isn't standing still. In fact, there are already 3 big waves on the horizon. Wave 1 learned PQ on GPUs. Libraries like FAIS and NVIDIA CUVS can now train product quantization codebooks directly on the GPU. That means they can crunch through billions of sample vectors in just minutes, not hours. And the next step, adaptive PQ. That's where each shard or segment learns its own codebook on the fly. So the hot parts of the data, the ones we search most often, can keep high recall, while the less used parts get compressed even more to save RAM. Wave 2 hardware acceleration is catching up. We're seeing instructions like POP-CNT and bit slicing grow wider, 256, 512, even 1024-bit lanes in the latest CPUs. On top of that, Apple's Neural Engine and Qualcomm's Hexagon already support XOR plus population count directly. That basically means that fast ham in search, using just 1 bit, is about to become a native feature on mobile chips. Wave 3 – New workloads. Retrieval augmented generation pipelines need to fetch context super fast, like within a couple of milliseconds, to keep large language models chatty and responsive. And honestly, quantized search is pretty much the only way to hit that kind of latency at scale. My colleague Dmitry Kuzminkov will dig into RAG in his talk later today, so definitely stick around for that. Now, on the other end of the spectrum, we're seeing something interesting. Edge devices like cars, drones, and even smart headphones are starting to carry tiny vector stores. They're using them for things like wake word detection or personalization. And here is the thing, they just don't have the power budget for full precision search, but give them a few megabytes of 4-bit or even 1-bit codes, no problem. They can handle that easily. So when you step back and look at the big picture, the trend is clear. Smarter codebooks, faster hardware, and more use cases than ever. Vector quantization isn't just about speeding things up in data centers anymore. It's heading toward making intelligent search common everywhere, from massive cloud LLMs to the phone in your pocket. Alright, before we wrap up, I want to give you a quick peek at what we've been working on at Manticore lately. We're currently adding several types of vector quantization, including a super compact 1-bit asymmetric method. It's already in closed beta and we're looking for people to try it out. So if you'd like to test it or run your own benchmarks, just let us know, we'd be happy to get you on board. Now here is how it performs in the quadrant benchmark on the DBpedia 1 million dataset. Precision 0.79, same as Elasticsearch's best and quite a bit ahead of Quadrant's 0.63. Speed around 400 queries per second, which is about 40% faster than Elasticsearch on the same hardware. Latency, median response time is under 4 milliseconds. And the cool thing is, Manticore isn't just a full-text engine with vector search bolted on. It's built as hybrid from the ground up. You get full-text features like phrase and fuzzy search, Boolean logic, geofilters, SQL-style queries, real-time indexing, and now fast and compressed vector search all in one place. Quantization is still under active development, but the early results are really promising. If you are curious and want to get early access, come talk to us. We'd love to have you join the beta. So, just to quickly sum things up, quantization has quietly become a key part of fast, scalable vector search. It helps cut memory usage, speeds things up, and lowers costs, all without losing accuracy as long as it's done right. Whether you're after some quick wins or ready to dive deep with product quantization, there is likely an option that fits your stack. And with smart techniques like oversampling and rescoring, you can still get great recall without paying the full price in precision. Thanks a lot for listening, and I'm happy to take any questions.